This video will be your Chapter 7 quiz review. All right, the first three problems on the Chapter 7 quiz tell you to write each expression in radical form. Here with 11 to the 1/2 power, anytime we look at a fractional exponent, we look at the bottom number of the fraction, determine the index of the radical. We use the top number for the power of whatever's going in here. So in this case, it's a square root. The 2 is understood. 11 to the power of 1. We don't have to write to the power of 1. There's our answer. For y to the 5/6, we look at 6. Again, the number on the bottom of the fraction, the denominator, will be the index of the radical. And then we're going to take y to the 5th power. Because 5 is less than 6, we do not need to reduce here in any way. With x to the negative 5/4, we have to first deal with the fact that we have a negative exponent. A negative exponent is the same as the same exponent on the bottom side of the fraction. So here we just rewrite as 1 over x to the 5/4. From there, looking at x to the 5/4, we realize that's a radical. So we need to eliminate that radical. If we had x to the 8/4, that would reduce to x to the 2nd power, and we'd have no radical on the bottom. So, in order to get to x to the 8/4, we're missing 3/4 x. So we're going to multiply top and bottom by x to the 3/4. This is the same as multiplying by 1, so we haven't modified the ratio of the fraction in any way. Then we multiply across. When we multiply two expressions with the same base and exponents, we can just add those exponents together. So 5/4 plus 3/4 is going to give us x to the 8/4. On the top, we'll just have x to the 3/4. Our last step will simplify. X to the 3/4, the 4th is the index of the radical. The 3 on the top of the fraction will be the power of x. On the bottom, x to the 8/4 is just x squared. And we're complete with a final answer right there. Page 2 of the quiz requires us to write each radical using fractional exponents. When you have a radical, we just look at the index to determine the bottom part of the fraction. So this is going to be 13 to the 1/2 because 13 is a prime number to the 1st power. So again, that 1 comes from the power on 13. The 2 here comes from the fact that we're taking a square root, comes from the index. Again, if it's blank here, it's an understood 2 for a square root. On number 5, we have the 4th root of x. The index of 4 is going to become the denominator of the fractional exponent. And again, the power of x will become the numerator on the exponent. We have x to the 1/4. In problem 6, they give us the following. We have the 4th root of 16 x squared y to the 8th. We're trying to move to a fractional exponent, so the first thing we can do is convert this radical to a 1/4 power. In other words, this expression here to the 1/2 power is same as this expression here inside of 4th root. And excuse me, that's not to the 1/2. It's to the 1/4 because, again, we have an index of 4, so that's going to be 1/4. All right. From there, we just need to apply the power to each piece of it. We can also see that 16 is 2 to the 4th. So we'll rewrite this way. 2 to the 4th, x squared, y to the 8th. All of this to the 1/4 power. We can then apply that power. So we're going to have 2 to the 4th to the 1/4 power, x squared to the 1/4 power, and y to the 8th to the 1/4 power. As we simplify across, 2 to the 4th to the 1/4, we just multiply each of our powers, so that'll just be 2. In this case, we're going to have x to the 2/4 or x to the 1/2. And here, y to the 8th to the, y to the 8 over 4 is going to reduce to become y squared. For number 7, the last problem on the page, they give us x cubed over the 4th root of z. We have a radical on the bottom that we need to eliminate. And again, to simplify our, and they're asking us to move into fractional exponents. So the first thing we can do is just rewrite as fractional exponents. The same as x cubed over z to the 1/4. We have z to the 1/4 on the bottom. We need to get a whole power of z to eliminate the radical. If we had z to the 4/4, that would be the same as z to the 1st power, so we're just missing 3/4. So we're going to multiply top and bottom by z to the 3/4. As we multiply across, on the top, we're going to get x cubed times z to the 3/4. On the bottom, we'll multiply here. That means we're going to add exponents. So we'll get z to the 4 over 4. That will then simplify to give us x cubed z to the 3/4 all over z. Now normally we would rewrite z to the 3/4 as a radical, but in this case the instructions expressly tell us to give an answer using fractional exponents, so that would be our final answer. Problem 8 on the next page asks us just to simplify each expression. So in problem 8, gives us x to the 1/4 times x to the 7/4. Here we add exponents because we have a common base. So this will be x to the 8 over 4. That is going to reduce down to x to the 2nd power. And there's our final answer. Number 9 asks for a to the negative 2/3 to the negative 3/4 power. Here, when we have a power to a power, we multiply exponents. So we'll have a to the negative 2/3 times negative 3/4. In this multiplication here, we can cross cancel. The 3 and the 3 will go away. The 2 and the 4 will reduce down to just a 2. The negatives will cancel. So we have a to the 1/2, which we then write as a final answer of square root of a. Number 10 gives us the 6th root of 8. anytime we have a numeric expression in a radical, we want to break that down into its prime factorization to see if any perfect squares, or in this case, sixth roots, can come out. So we'll rewrite this as the sixth root of 2 cubed, since 8 is 2 cubed. Now, at this point, we can rewrite this as a fractional exponent. Again, the index will form the denominator of the fraction. The power on the number inside the radical will form the numerator. So we get 2 to the 3 over 6, which is going to reduce to 2 to the 1/2. Which just simplifies down to the square root of 2. The next page, with numbers 11 and 12, the instructions remain the same. Just simplify each expression. All right, so there's the initial problem for 11. We can convert the radical into a fractional power. And at the same time, we can convert the 8 into 2/3 again. So the 8 will become 2 to the 3rd power. Y to the 6 z cubed remains the same. But all of this is to the 1/6 power because we're taking a 6th root. Now we'll just apply that power across. So when we when we have a power to a power, we just multiply. So we'll have 2 to the 3/6 times y to the 6 over 6 times z to the 3/6. Each of these powers we can simplify. We'll get 2 to the 1/2 times y to the 1st power times z to the 1/2. And then again, we just rewrite all of this in radical form. 12 is a little bit more complicated. Here, we need to convert these into prime factorizations and rewrite, then take those powers to simplify here. So 8 we can rewrite as 2 to the 3rd to the 1/6 minus 25 is really just 5 squared. So 5 squared to the 1/4. We'll leave in place our radicals here on the bottom for the moment. This is going to be 2 to the 3/6, or the square root of 2. Similarly, this is going to be 5 to the 2 over 4, or 5 to the 1/2, so the square root of 5. So we can rewrite this as such. Now at this point, in order to eliminate a binomial radical on the bottom, we're going to need to multiply by the conjugate. For the conjugate, we just look at what we have in the denominator and change the sign. Otherwise, it will remain the same. And we'll multiply top and bottom by that conjugate. We're then going to FOIL out top and bottom. Here we're going to get root 2 times root 5 gives us root 10 on the top. Outer terms, we're going to get root 2 times negative root 2. That's just going to be minus 2. Here, negative root 5 times root 5 is going to give us negative 5. And lastly, we'll close out with negative root 5 times negative root 2 gives us positive root 10. On the bottom, this is a difference of squares. As we pay attention to that, it looks like the form of x plus y, x minus y. So we can just square the first term and subtract off the square of the second term because we have a difference of squares. So we're going to get 5 minus 2 because square root of 5 squared gives me 5, square root of 2 squared gives me square root of 2, and we're going to subtract because we have a difference of squares. We'll now combine like terms. Here, on top, we'll end up with negative 7. We have 2 copies of root 10, so those will add together to be 2 root 10. On the bottom, 5 minus 2 will give us 3, and that will be our final answer. The next page asks us to solve each equation. And here we're going to have radicals in our equations. The first thing we want to do when we have a radical is isolate the radical if possible. Subtract 9 from both sides. End up with the radical 4y minus 4 equals 3. There, we can square both sides to eliminate the radical on the left-hand side. We'll get 4y minus 4 equals 9. We can add 4 to both sides. So we get 4y equals 13. Divide both sides by 4, and we'll get y equals 13 over 4. But now we'll need to check and make sure that that answer is not extraneous. So we'll take that 13 over 4 and replace it into the original equation. Internal to the radical, we can see that this 4 will cancel with that 4, so we'll get 9 plus the square root of 13 minus 4 is equal to 12. Simplify there. We're going to get 13 minus 4 gives us 9. So we've got 9 under the radical. That's, of course, 3, so we're going to get 9 plus 3 equals 12, or 12 equals 12. And we can see that our equation checks out. Problem 14 gives us a similar problem. Again, the first step that we want to do is isolate the radical. So we'll subtract 7 from both sides. We get that expression. We'll square both sides to get rid of the radical, leaving us with 2x minus 1 on the left, 1 on the right. Now we solve for x normally. Divide both sides by 2, we're going to get x equals 1. Again, because we are dealing with radicals, we have to check for extraneous solutions, so we'll enter our x value of 1 into the original equation to see if it works. Two times 1 will be 2 minus 1 just gives us 1 inside the radical. Square root of 1 is just 1. And so the problem checks out. $15 is a little bit different because now it involves a radical that's taking a cube root. In this case, the procedure is generally the same. We want to isolate the radical. We'll just be cubing both sides rather than squaring both sides. So again, the first thing we will do is get the radical by itself. We get a -2 there. Now we're going to cube both sides to eliminate the radical rather than squaring both sides because we need a cubed power to get rid of a third root. Leaving us 3x minus 6 equals -8. Again, we can solve for x normally at this point. (3x equals -2). Divide both sides by 3, and we're going to get x equals -2/3. We'll now take that answer and again perform our normal check to make sure we do not have an extraneous solution. From here we can see again that the 3 here will cancel with the 3 on the bottom. That leaves us with the cube root of -2 minus 6 plus 5 equals 3. This is going to be the cube root of -8. Cube root of a negative number is no problem, right? Anytime we have an odd-powered index, we can still deal with that. It does not generate an I for us, so this is just going to be -2 is our cube root here. Those are going to add up to 3, and we see that the problem checks out. All right, as we move to the next page, 16 and 17 now ask us to solve inequalities. And remember, with inequalities, we have a couple steps that we have to go through. One, to make sure that we don't have a impermissible value inside the radical, and then we will solve for the variable normally and then test to make sure those values work out okay. Here's our original problem. The first thing we want to do is take just the radicand, whatever's inside the radical, and set it greater than or equal to 0. So that would be our step 1, is take the radicand, x plus 2, set it greater than or equal to 0, and solve for x there. Here we're going to see that x must be greater than or equal to -2, so that's going to be our first restriction. Now, in step 2, we're going to go ahead and solve normally for x. So we're going to take the whole original equation and we will solve for x. Again, we'll need to isolate the radical. square root of x plus 2 is less than 5. We'll square both sides to get rid of the radical and be left with x plus 2 is less than 25. Subtract 2 from both sides. And we get x is less than 23. We're now going to combine those restrictions to give our total full answer. So we have this initial restriction from the limitations on what could go in the radical. We have this second restriction here from solving from the variable normally. We'll combine that in step 3 to give an answer of negative 2 is less than or equal to x, which is less than 23. To help us visualize that, we can graph it if we want. We'll have a closed circle at negative 2 because it's a permissible value. At 23, we'll have an open circle because x must be strictly less than, and then we see that we're going to have all the solutions in between those two values. In step 4, we'll now do a check by putting in a test value in each of the 3 regions. We need some value less than negative 2, some value in here in between negative 2 and 23, and some value greater than 24. If we choose x equals negative 3, that should give us a false value because it's outside of the solution set. We're going to plug that into the original equation. So here, instead of x plus 2, we're going to put in negative 3. Negative 3 plus 2 plus 4 outside the radical is less than 9. Right away, we can see we have a problem here because this becomes negative 1 in the radical. We're not able to do that, but that would generate an imaginary number, so we can immediately say that that solution is false, which gives us exactly what we wanted. Now, we need to pick a value inside the solution set. We can choose x equals 1. That's clearly greater than negative 2 and less than 23. When we do that and put it into the original equation, we go like that. We're going to get the square root of 3. Square root of 3 plus 4 is less than 9. Well, we know the square root of 3 is less than 2. You can put it in your calculator and see what value you get, but clearly this is going to be a true statement, precisely the way we expect it to be. So that works out just fine. Now, for our value out here, we'll pick x equals 34 just because it'll make the calculations nice. And this should give us a false answer if we've done this correctly. Put in 34 for x. Here, this is going to be the square root of 36, which is really just 6. So we can say 6 plus 4 is less than 9. That's clearly false because 10 is not less than 9, and it gave us the false answer that we were looking for. All right, 17 introduces a little bit of a complication because now we have 2 radicals. And again, generally speaking, what we want to do is try to isolate the more complicated radical first, and then go from there. But before we even get to that, remember our step 1, when we have an inequality with radicals, is we need to set both of our radicands, both this one of x and this radicand of x plus 10, we set both of those greater than or equal to 0, and then determine which of those restrictions we need to abide by. This one, obviously, no work to be done. Here we subtract 10 from both sides, and we see that x is greater than or equal to negative 10. Then the question we have to ask is, which of these is more restrictive? Well, if we went by this restriction, negative 9 would be permissible. That certainly would work here in this radical. Negative 9 plus 10 would be 1, right? That would be allowed under there. But if we put that same negative 9 in over here, we see we have a problem. That would give us an imaginary number, so that cannot be the restriction that we're going to use. Instead, we'll use the more restrictive value here. Anytime we're in abeyance of x is greater than or equal to 0, it certainly works here, but it will also work here. So this will be our initial restriction for step 1 of our calculation. Now, in step 2, we'll go and solve for x normally. Again, we want to isolate the most complex radical if we can, so we'll add square root of x to both sides. From here, we can now square both sides to eliminate the radical. Well, this side simplifies nicely. This side, we're going to have to FOIL this out, because this is really this term times itself. When we FOIL that out, because this is just a square, we can do this fairly quickly. We can square this term. 2 squared is 4. We multiply these times each other and double them. So rather than having just 2 root x, we'll have 4 root x. And lastly, our last term, multiplication of FOIL, would give us square root of x times square root of x, or just plus x. Now we need to continue to simplify and isolate the remaining radical so that we can solve there. We're going to see that the x's eliminate right away. There's an x on both sides, so we can just subtract off x and those go away. We now want to combine the numeric portion to isolate that, so we can subtract off 4 from both sides, and we'll end up with 6 is greater than 4 root x. At that point, we just divide both sides by 4. 6 divided by 4 is just going to give us 3 halves is greater than the square root of x. We can square both sides to eliminate the remaining radical, and we'll get 9 over 4 is greater than x. We're then going to combine the 2 restrictions we've had. From step 1, we know that x is greater than or equal to 0. From step 2, we know that 9/4 is strictly greater than x. So in step 3, we'll combine those. And write it like that. Again, we can graph that out if we want, but the key is in step 4, just taking a value from each of the 3 regions. We want something less than 0, we want something within the region, and we need something bigger than 9/4 outside of the region to the right. In this case, I'll use x equals -1 for something to the left of this, in the region that would not have an answer. We expect to get a false answer here. And again, we see we get that right away. We put a -1 in here. We don't need to go any further because we have a negative inside of a square root. That's going to give us an imaginary number, so we can immediately say that that's false, just as we expected it to be. Inside the region, we'll choose x equals 1 because x equals 1 is clearly greater than or equal to 0 and less than 9/4. So square root of 1 is just 1. We've got a minus in front of it, so we'll have negative 1 plus the square root of 11 is greater than 2. We can add 2 to both sides, or excuse me, add 1 to both sides. So we're going to get the square root of 11 is greater than 3. Well, we know that's true because square root of 9 would give us 3. Square root of 11 is going to be larger than that. So even without looking at our calculator, we can clearly see that this is a true statement as we expected. Lastly, we can choose, again, any value greater than 9/4. 9/4 is the same as 2 1/4, so we'll just choose x equals 3 as our test value. And we should get a false statement here if we've done our work correctly. Take those values. Again, we can use your calculator, punch in those values, and you'll clearly see that that is a false statement when we subtract the square root of 3 from positive square root of 13. That's going to be less than 2, actually, and that'll give us a false statement. All right, the next section of the quiz asks us to start dealing with operations of functions. We're going to add functions together, we're going to multiply functions, and we're going to take the composition of functions. So for 18 through 21, we're going to use the following two definitions. G of x equals x minus 4, and h of x equals x squared. 18 asks us for the new function g plus h of x. Well, all that requires us to do is take g of x and add it to h of x. Well, here g of x is just x minus 4, so we have x minus 4. We'll add that to h of x, which is just x squared. And then we can simplify. We would write our polynomials from highest power to lowest power in a final form. X squared plus x minus 4 would be our final answer for 18. 19 asks us to create the new function g times h. The function g times h of x. So we will just multiply the two equations times each other. What this means is g of x multiplied by h of x. Remember, this is a function, we're going to multiply them. So we're going to take x minus 4 as g, multiply it by x squared, which is h. We'll just distribute the x squared. So here we're going to get x squared times x gives me x cubed. X squared times negative 4 gives me negative 4x squared. It's already written in the correct order of highest power to lowest power, so we're all set with a final answer. 20 now asks us to do the composition of functions. And it asks for g composed with h. And again, what this means is we're going to take the function g, but it's going to get a new input of h. Well, h of x is just x squared, so the new input for g is x squared. G normally says x minus 4 would be the value, but we're going to take this new input x squared and replace every instance of x with that. So we're going to get x squared minus 4. 21 asks for the other composition. It asks for the composition of H composed with G. So we're changing the order of composition. So that now says the function H will take the function of G as its input. Well, G of X is X minus 4. So that says H is going to have an input of X minus 4 instead of just X. When we do that, we put X minus 4 into every value of X for H. So rather than getting X squared, we're going to get X minus 4 squared. And if you chose to FOIL that out, certainly no problems there. That would just be X squared minus 8X plus 16, also an acceptable answer. The next page, problems 22 through 25, are similar to the previous page. It's going to be the same operations, but with two different functions. We have a new G and a new H in this case. But it will ask us to perform the exact same operation. So I'll leave those operations up in place. And the new G for these problems is going to be negative 4x. The new H of x is 3x squared plus 2x plus 1. Now we'll go through the same procedure. Here we're doing G plus H, so that's just going to be the function G of x plus the function H of x. So in this case, we're going to have negative 4x plus this whole piece here, 3x squared plus 2x plus 1. We'll combine like terms to simplify and write in the order of highest power terms first. So 3x squared has nothing to combine with. It'll be just 3x squared. Negative 4x and 2x will combine to be negative 2x. And 1 has nothing to combine with. We'll just add that 1, and there's the final answer. Here we have G times H. So we're going to do negative 4x times H, which is 3x squared plus 2x plus 1. So we multiply across. We're just going to distribute this negative 4x all the way across. We'll get negative 12x cubed. Then we'll go here. We'll get negative 8x squared. And lastly, negative 4x times 1 is going to give us negative 4x. There would be our answer for G times H of x. We get down to the composition of functions here. Again, this means G, where its new input is the function H of x, which is the same thing as G with this as its input. Well, G just means multiplication by negative 4. So instead of negative 4x, we're going to have negative 4 times all of that. And so we're left with negative 12x squared minus 8x minus 4. So notice these answers are similar but different. They're each a slightly different operation that gives us a slightly different answer. For H of H composed with G or H of G, we're going to do the same process with a different order of which function is going in. So H of G of x says we're going to take H but input G of x, meaning negative 4x, everywhere that x would normally go. So at that point, we're going to take our G and have 3 times negative 4x squared plus 2 times negative 4x plus 1.
We do that multiplication across, and we have to be careful here. We're going to square by PEMDAS. We've got to do exponents first before we get to the multiplication. So we'll square this. So this is going to become 16x squared. 16x squared times 3 is going to give us 48x squared. Here, we're going to have a negative in here, right? So we're going to end up with negative 8x. And again, the 1 had no input, so it doesn't get modified in any way. So there is our final answer. Oh, and I should have, apologies, I should have relabeled these with the numbers. Those, of course, were problems 22, 23, 24, and 25. So if there was any confusion there, that was 22 through 25. All right. The next two questions ask us to deal with inverse functions. (26) asks us to find the inverse of f of x equals 2x plus 1. Here we go through our normal four-step process. Step 1, we're going to rename the function to just reintroduce y. So we rename this y equals 2x plus 1. Step 2, we're going to exchange x and y in the equation. So we now get x equals 2y plus 1. In step 3, we're now going to solve for y again. So we'll take this equation, we'll solve for y, which means we need to isolate y. So we'll get x minus 1 equals 2y. Divide both sides by 2. And we get x minus 1 over 2 equals y. Step 4, we're just going to rename this and call it f inverse. So step 4, we'll say f inverse equals x minus 1 over 2. Lastly, we'll do our check. To do a check, we take the original function f, we compose it with its inverse. If the composition comes out to be equal to simply x, then we've done the inverse calculation correctly. F composed with f inverse means we're going to take the function f, and it's going to have a new input of the inverse function. That's the same thing as saying x minus 1 over 2 will go in for the input for f. Now we apply f where this goes in and replaces x. As we do that multiplication, we see these 2's are going to cancel, leaving with x minus 1 plus 1, giving a final answer of x. And that is a valid check that we have calculated the correct inverse. (27) asks us to do the same thing with a different function f. And in 27, our function f is negative 2/5 x plus 2. So again, we'll go through the exact same four-step process plus a check. Step 1, we'll rename this function, reintroducing y. So y equals negative 2/5 x plus 2. Step 2, we'll exchange x and y. Now in step 3, we'll solve for y. We can subtract 2, well, let's rewrite it. We'll subtract 2 from both sides. Now here, we're multiplying y by negative 2/5 initially. So what we can do is just multiply by the reciprocal. We can get rid of negative 2/5 and leave y by itself if we multiply this whole piece by negative 5/2 instead. We've, of course, got to do the same thing to the other side. This side is going to leave us, as we distribute this across, we're going to have negative 5/2 x. Negative 5/2 times negative 2. The 2 on the top and bottom will cancel. The negatives will cancel. We'll get plus 5 equals y. So step 4, we can rename this as F inverse. F inverse equals negative 5/2 x plus 5. And lastly, we'll go through a check to make sure that the answer that we've given here in step 4 is correct by composing the functions again. This just means we're going to take f with a new input of F inverse. Well, F inverse is just what we've written right here. When we put that into the original function f, we see it's going to look like this. Negative 2/5 times x, but this whole piece here will become x. Plus 2. We multiply across, distribute this negative 2/5 here. That negative 2/5 and the negative 5/2 will cancel, leaving us with just x. Negative 2/5 times 5, the 5 on the top will cancel with the 5 on the bottom, giving us minus 2. And we still have a positive 2 out here. That's going to simplify down to just x. And so again, it shows that we have correctly calculated F inverse as negative 5/2 x plus 5. All right, 28 and 29 are similar, but instead of calculating the inverse, they give you two functions and then ask whether they are inverses of one another. And so what we'll do, rather than calculating an inverse, we'll just take the composition of the two functions directly and see if it comes out equal to x. The only answer we have to give after showing our work is yes or no, whether or not they are inverses. So 28 f of x equals 5x plus 3. G of x equals negative 4x minus 2. To determine whether or not these are inverses, we just take their composition. Go through our normal composition process. F composed with G means the same thing as F with G as its new input. G is negative 4x minus 2. F is 5x plus 3, so we're going to have 5 times this new input, negative 4x minus 2 plus 3. We continue to simplify. We distribute the 5. We're going to get negative 20x minus 10 plus 3. Combine like terms, negative 20x minus 7. Clearly that is not equal to x, so no, these two functions are not inverses of one another. (29) asks us to go through the same process, but with two different functions. Our f of x in this case is 4x plus 2. This is problem 29. and g of x is x minus 2 over 4. So again, we'll take this composition and look to see if it equals to x. F composed with g is the same as f with an input of the function g. That's just our definition of composition. So we have f where g of x, x minus 2 over 4, is our input. Now we apply the function f. So we have 4 times this new input, x minus 2 over 4 plus 2. As we simplify, the 4 here, the 4 there will cancel, leaving us with x minus 2 plus 2, or x. So here, clearly, the answer is yes. The functions are inverses of one another.
The last equation, or the last problem on the quiz, asks us to graph an inequality, or excuse me, graph a square root equation. And I'm going to take a second and pull up Desmos here so we can graph this one with Desmos as our graphing chart in the background. All right. So for number 30, we are asked to graph. Let's see, make sure I stay within my writing zone here. 30 asks us to graph the following equation with a radical in it. Y equals square root of x plus 6 minus 3. We need to see where that's going to go. So the first thing we want to do is always look at what's inside of our radical to determine where's this square root value function going to start. In other words, what are the beginning of permissible values? So we take x plus 6, we set it equal to 0. We can subtract 6 from both sides to say x equals negative 6. So that's going to be where we're going to start with our table of values. We can then set up that table of values. And of course, y is going to be equal to this equation that they've given us. We can pick some x values. And here, because we're going to be taking square root, I want to be smart about the x values that I pick. I want them to essentially work out to have perfect squares if possible. In this case, we can do that. Clearly, if we put in negative 6 for x, in that case, this is going to be negative 6 plus 6 is 0. Square root of 0 is just 0, so we just get negative 3 for our y value. But again, what we can do is kind of be smart about our choices of x values. And let's pick values that will give us nice numbers when we plug them in here. So if we put in negative 5, we're now going to get negative 5 plus 6 in the square root minus 3. Well, this is just going to be 1. The square root of 1 is just 1. So 1 minus 3, that'll give us negative 2 for our corresponding y value. We'll now make the jump to negative 2 because, again, notice what's going to happen there. If we put negative 2 in, negative 2 plus 6 minus 3, we're going to get negative 2 plus 6 is 4. Square root of 4 is just 2. 2 minus 3 is just going to give us negative 1. So we're going to continue to get nice values that are easy to graph. Thinking, again, what's the next value that will give us something nice in this expression? Okay, if we put in 3 for x, 3 plus 6, that would give us 9. That's got a perfect square root. So 3 looks like a good next value for x. If we put in 3, we get 3 plus 6, all minus 3. This is the square root of 9, or just 3. 3 minus 3 is 0, and we get another nice value to graph. If we wanted to go even one further, we could. I think this will go off our graphing chart of what you can see on the screen, but we'll just go ahead and do it. 10. An x of 10 also gives us a nice value. We do the calculation. We're going to put in 10 plus 6 under the radical, all minus 3. Well, that's going to be square root of 16, which is just 4. 4 minus 3 would give us positive 1.
So that gives us a pretty good selection of x, y values. So now we're just going to graph each one of these points. So I have the point -6, -3. Come over here to -6, go down to -3. There's my first point. There's the beginning of my graph. We know that there's nothing to the left of that because of this calculation we did here. Anything else to the left of that would give us a negative value inside the square root. And then we can continue to plot. -5, -2. -2, -1. 3 and 0. X equals 3, y equals 0. Lastly, we got x equals 10, y equals 1. And this probably goes off what you can see on the video, but I'll plot it in there, and then we just connect up those points to create our graph. And there would be our graph for number 30. All right, lastly, we'll go through the extra credit problems. All right, extra credit A asks us to simplify the following expression. X plus 1 all over the square root of x squared minus 1. All right, well, we know we can't leave a radical on the bottom, so we need to rationalize the denominator. In order to do that, we can just multiply the top and bottom by this radical right here. So we'll multiply top and bottom by square root of x squared minus 1. So on the top, we'll just leave it right like this for a second. We'll leave it as x plus 1 times this radical, x squared minus 1. On the bottom, we're going to get x squared minus 1 because the square root of anything times itself is going to give you what was inside the radical. From there, we can factor the bottom part. We notice this is a difference of squares. So the top will remain the same, x plus 1 times the square root of x squared minus 1. On the bottom, this is a difference of squares, so it's going to factor as x plus 1, x minus 1. Now we can see they have a factor in common. We can cancel like that, and our final answer would be the square root of x squared minus 1 all over x minus 1. Extra credit B asks us to take the fifth root, let me make sure that's clear, the fifth root of the square root of 32. Well, let's convert this into fractional exponents to simplify our calculations. The fifth root is the same as taking something to the fifth power. So we could say that's the same as the square root of 32 to the 1/5 power. Okay? And not to the fifth power, to the 1/5 power. Excuse my misspeaking there. 32, the square root of 32, well, 32 is 2 to the 5th. So we can rewrite the 32 as the square root of 2 to the 5th. All of this is to the 1/5. But we can rewrite this in exponent form as well. This is the square root of 2 to the 5th. So this is 2 to the 5th over 2, but all raised still to the 1/5 power. Here, a power to a power, we can just multiply exponents. So we're going to get 2 to the 5 over 10, which we simplify to the 2 to the 1/2, which again we can just write as square root of 2, and that's our final answer. Because we always want to give answers in radical form unless the instructions say otherwise. All right, finally, we're going to get to extra credit problem C. And this one asks us to find the composition of f and g, two different functions. Okay, f of x equals x to the 5/3 power. G of x equals x minus 2 to the 3rd power. And the question asks us to find the composition of f with g. Well, that's just the same as f, where g is the input. So g is x minus 2 cubed. And our parentheses get a little strange here. Just keep track of them in that way. But now what this says is we're going to take whatever this is and raise it to the 5/3 power. So we're going to get x minus 2 cubed all to the 5/3 power. Well, here we're going to multiply exponents. The 3 is going to, on the top, in the numerator here, is going to cancel with the 3 in the denominator there. So this is really just x minus 2 to the 5th power. Once we see that, according to the hint, we can just use the binomial expansion to find our final answer. So we use our binomial expansion. Start out our pyramid with 1 and 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and lastly we need the 5th row because we're going to the 5th power, so we'll do as such. 1, 5, 10, 10, 5, 1. Now, we'll initially use this with just x plus y to the 5th, so x plus y to the 5th would be, according to our normal process, x to the 5th plus 5 x to the 4th y plus 10 x cubed y squared plus 10 x squared y cubed plus 5 x to the y to the 4th, or times y to the 4th, plus y to the 5th. All right, so we still have a little bit of work to do because we did a general x plus y, and our y value is really -2. So everywhere that we have a y value, we need to substitute in -2. So x minus 2 to the 5th is going to be x to the 5th plus 5x to the 4th times -2 plus 10x cubed -2 squared for y squared plus 10x squared -2 cubed for y cubed plus 5x times -2 to the 4th plus -2 to the 5th. And here we can finally combine all this together. So we're going to have x to the 5th plus. Now we've got a -2 here, so that it's not going to be a plus, right? It's going to be a negative. -10x to the 4th. Here, we're going to have -2 squared is going to be +4, so the negative is going to go away. We're just going to multiply 4 times our 10, so we're going to have 40x cubed. Here, -2 cubed is going to give us -8, so we're going to have -80x squared. Here, -2 to the 4th is going to be +16, right? All those negatives are going to be canceled since we're raising to an even power. And so 5x times 16 is going to give us +80x. And lastly, we have -2 to the 5th power. That one is just going to be -32. Again, we're to an odd power, so the negatives will remain -32.
And that would be our final answer for extra credit, problem C. We'll see you guys in class soon.